Assalamualaikum and selamat sejahtera to all the lecturers. Today we will be presenting our lab report on electronic dice roller. So our team has four members, which is Farzana, the leader, Jafira, Aisha, and Fatin Hasna. In chapter 1.1, we will discuss about our introduction. A digital substitute for conventional dice, an electronic dice roller is made to produce a random number between 1 and 6. Quarters 2 and Altera DE board are used in its implementation, guaranteeing an impartial and equitable rolling experience. The way the system works is that a button is pressed to select a random number, which is then shown on a 7-segment display. If the number stays the same, the user has to click the button again until it changes to a new value. Common problems with traditional dice, such as unfair rolling, loss, or wear over time, are eliminated by the electric dice roller. It offers a dependable and effective solution for probability experiments, board games, and other applications that call for the creation of random numbers. This project uses digital logic circuits to guarantee unpredictability and accuracy, making it useful and creative substitute for traditional dice. Electronic dice systems have developed over time to improve game experiences and increase dependability in a range of applications. Next, 1.2, we will discuss about our problem statement. Despite their widespread use in games and probability-based applications, traditional dice have a number of disadvantages. Due to the flaws in their shape or rolling surface, physical dice can be misplaced, tampered with, or yield biased results. Furthermore, manual rolling can occasionally result in disagreements about fairness. An electronic dice roller is suggested as a computerized, impartial, and trustworthy solution to these problems. These ideas offers a practical and long-lasting solution while guaranteeing randomization and fairness in random production through the use of digital logic circuits. 1.3 is our objective. First, to develop an electronic dice roller system sequence. Second, to generate a random number between 1 and 6 using a counter, JK flip-flops, and shift registers. Third, to display the output on a 7-segment display for easy readability. Fourth, to incorporate a push button as the trigger for rolling the dice. Fifth, to ensure randomness and fairness in number generation through appropriate digital logic design. Sixth, to design and implement an electronic dice roller using Quarters 2 and Altera DE board.
For scopes of works, this project involves the design of digital dice using Quarters 2, 8.1 web edition, which include 4 people discussing the state diagram, JK flip-flops, transition table, truth table, and K-map mapping for the selected project. 2 people volunteering themselves go to the lab for DE board testing.
Assalamualaikum. So it's me, Jafira. So I will be explain about this chapter 2. So as you guys can see, this is the state diagram for the dice counter that cycles through the numbers 1 to 6, binary 001 to 110. So each time the button is pressed, acting as a clock signal, the counter moves to the next state. Once it reach 110, which represents 6, it resets back to 001, which represents 1, and continues the cycle. And this is the growth table that we could get from the state diagram. It shows that the counting will start from 1 and then go to 6 and will reset back to 1. And this is the transition table. X is X as clock, and that's, and yeah, and this is the care map that we could get from the transition table, and also Boolean expressions derived from the care map. So there are 6 care map because 3 flip flops, and there is 6 flip flop inputs here. So the grouping for the for the J2 is like this. So the Boolean expression will be Q1 and Q0. And for J1, the grouping is like this. So the Boolean expression will be Q0. And for J0, the grouping is all of this. And the Boolean expression will be Q0 bar plus Q0 or just one. And for K2, the grouping is like this. So the Boolean expression is Q1 and K1. The grouping is like this and this. So the output will be Q2, the Boolean expression will be Q2 plus Q0. And this just same like J0, which is the grouping is all of this. So the Boolean expression will be 1 or Q0 bar plus Q0. That's all.
For chapter 3, I will tell about schematic diagram and waveform. For schematic diagram, this circuit presented is a 3-bit synchronous counter using JK flip-flops, designed to function as a Mod 6 counter for a dice rolling simulation. The circuit consists of two identical counters, one for each player. Ensuring independent dice rolls, each counter cycles through 6 state 1 to 6 before resetting, mimicking the behavior of a standard 6-sided. The circuit is driven by a clock signal that synchronizes the state transition of the flip-flops. The output are then fed into ABCD to a 7 segments decoder, which convert the binary values into a format that can be displayed on a 7-segment display. Players roll their dice using button 1 and button 2, which serve as input controls for triggering their respective counters. To enhance gameplay fairness, the circuit includes special LED indicators, LED-G and LED-G1. This LED lights up when a player rolls a 6, signaling that they must roll the dice again. For LED-G and LED-G1, we are using green LED. For detector, these circuits use an X-no based detection system to check if both players roll the same number. The Q0, Q1, and Q2 outputs from both counters are combined using X-no gates to compare the results. If both players get the same value, the detector turns on, indicating that the last player must roll again to break the tie. For detector, we are using red LED. For waveform, at the start, both counters remain at 0, meaning that neither player has rolled the dice yet. When a player presses the button, their counter begins counting based on the clock pulse. As the clock cycles, the output A, B, C, D, E, F, G change sequentially, representing the dice values for each player. Since the circuit uses a 7447 BCD, the output logic is active low. This means that when a signal is 0, the corresponding segment of the 7-segment display is turned on. Conversely, when the signal is 1, the segment remains off. The waveform reflects this behavior where a 0 outputs mean the respective segments are lit up, forming the correct numerical display corresponding to the dice value. For testing and troubleshooting, at first we built the circuit for only one player, However, the output waveform did not appear as we expected. We tried adding some logic gates, such as AND and OR, to the 7-segment display, but the output waveform still did not work as intended. Our lecturer suggested that we place output on each JK flip-flop, specifically Q at Q0, Q1, and Q2. Finally, the outputs appeared as expected. In addition, since we were making a dice roller, we needed a very high clock frequency to ensure that when a player pressed the button, the numbers spin randomly. We tried using 1 Hz and 100 Hz to find a suitable clock timing, but the numbers were still changing too slowly. After getting advice from several lecturers, they recommended that we use the pin planner as usual, specifically pin N2 with a 50 MHz frequency for the first circuit and pin D13 with a 27 MHz frequency for the second circuit. That's all for testing and troubleshooting.
For the discussion, this project aims to create a digital dice roller using an Altera DE2 board and involves several key components like the linear feedback shift register for random number generation, a push button to trigger the dice roll, a debound circuit for stable button input, and a 7-segment display to show the dice result. The most important part of the system is the LFSR, which is used to generate random numbers between 1 and 6. The number generated by the LFSR simulates the outcome of rolling a real dice. By adjusting the length and feedback tabs of the shift register, we can ensure the LFSR produces a suitable range of values, in this case from 1 to 6, to match the size of a typical dice. Once the random number is generated, the result is shown on a 7-segment display. The display is used to visually represent the number from 1 to 6, making it easy for the user to see the result. This project was developed using Quartus, a software tool that helped design, simulate, and implement the FPGA system. With Quartus, we were able to test the system's functionality before running it on the actual hardware, ensuring that everything worked as expected. For conclusion, this project successfully demonstrates the design and implementation of a digital dice roller using an Altera DE2 board. By using a linear feedback shift register, we were able to generate random numbers between 1 and 6, simulating a real dice roll. The push-button interface allows users to trigger the dice roll, and the debound circuit ensures that the input is stable and reliable. The 7-segment display effectively shows the result of each roll, making the system interactive and easy to use. Overall, this project highlights the advantages of using FPGA for hardware-based random number generation, providing a fast and efficient solution. Using Quartus for design and testing allowed us to validate the system's functionality and ensure its correct operation on the Altera DE2 board.